Hello and welcome back to another video. In this example problem, what we have here is an initially open container with a total of 1 kilograms of water in it at an initial temperature of 298 kelvins and an initial pressure of 1 atmosphere or 101,325 pascals. Now, what we do here in this situation is close this container and completely seal it off so that no air or water vapor can escape, and we heat the container up to a final pressure of 200,000 pascals or 2 bar, and the number of moles of water in the vapor phase at the end is equal to 0.3. Now, what we're asked to solve for in this example is the final temperature that we heat the container up to and the total volume of the container. Now, in order to solve a problem like this, since we will have two equations with two unknowns, we will be utilizing the root solver in Python to actually do the calculations. But before we hop into there, what we need to do here is relate the data that we have been given with the variables in this example to show the relationships. So starting off here, what we can do is look at the total volume of the container. Now we know the total volume of the container will be the volume of the liquid plus the volume of the vapor. So we can go ahead and write that in. So I have the total volume equals the volume of the liquid plus the volume of the vapor. Now going along with this, what we can also say is that the total mass of water will equal the mass of water in the liquid phase plus the mass of water in the vapor phase. So we can go ahead and write that in. So the mass of water total equals the mass of water in the liquid phase plus the mass of water in the vapor phase. Okay? Now the next thing that we can take a look here is this number of moles of water in the vapor phase. Now we know that the number of moles of water in the vapor phase will equal the mass of the water in the vapor phase divided by the molecular weight of water. So we can write that in. So I have the mass of water in the vapor phase divided by the molecular weight of water, and I will be inserting this in kilograms per mole. So I have 18 times 10 to negative third kilograms per mole. Now I know that this is probably hard to see since it is stuck up in the corner here, so I'll go ahead and repeat that for you. This is the mass of water in the vapor phase divided by the molecular weight of water, which is 18 times 10 to the negative third kilograms per mole. Now, another thing that we can look at here is this final pressure. Now, actually, before we talk about that, what I would like to just mention is that this is a situation here where we can utilize the ideal gas law since the molecules aren't seeing each other. So that's something that we can utilize going forward. Now, taking a look at this final pressure here, we can say that the final pressure of this system will equal the pressure of both the air in this container plus the pressure of the water vapor. So we can say that the final pressure here equals the partial pressure of the air plus the partial pressure of the water. And again, like I said, we will be able to utilize the ideal gas law here in this example, so we can actually use that here for the partial pressure of air. So here we'll have that the partial pressure of air, and utilizing the ideal gas law PV equals nRT, we'll have the number of moles of air times the ideal gas constant R times our final temperature divided by the volume of the vapor phase. Okay? Now for the partial pressure of water, we can actually utilize the Antony equation here, since the liquid water here actually exerts a certain vapor pressure at a given temperature. We can utilize the Antony equation. So here, for the partial pressure of water, using the log rules in the Antony equation, we'll have that the partial pressure of water will end up equaling 10 to the A minus B over the final temperature plus C. Okay? So now we have these relationships here. Now, another thing that we can look at is this volume of liquid. Now we know that the density equals mass divided by volume. So here we can say that the density of water equals the mass of the water in the liquid phase divided by the volume of the liquid. So since we already know the molecule or the mass of water in the vapor phase, we can go ahead and say that the mass of water in the liquid phase will be equal to the mass of water total minus the mass of water in the vapor phase. So we can say that there. So the mass of water total minus the mass of water in the vapor phase. Again, that is the mass of water in the liquid phase. So this will all be divided by the volume of the liquid phase. So here with this equation, we can also see that the volume of the liquid phase would then equal the mass of water total minus the mass of water in the vapor phase divided by the density of water. Now, what you may notice down here in this equation is that we don't necessarily know the number of moles of air in this system. But if we take a look here, we can actually write an equation for this if we take a look at the beginning of this situation. Now at the beginning here, the partial pressure of air will equal the total pressure minus the partial pressure of the water vapor that's in the container. So we can actually utilize that here with the ideal gas law. So we'll have the partial pressure of air will equal the total pressure at the beginning, so PI, the total pressure at the beginning, minus the partial pressure of water at the beginning. And again, this will be at the initial temperature, so the partial pressure of water at the initial temperature. Okay? And this will be multiplied by the volume of the vapor phase. However, what we can say here is that the volume of the vapor phase equals the volume, or the total volume, minus the volume of the liquid phase. So we can insert that here. So we'll have the total volume, and we know that the volume of the liquid phase equals the mass of water total divided by the mass of water in the vapor phase divided by the density, the mass of water total minus the mass of water in the vapor phase divided by the density of water. However, since we are assuming that the amount of water that we have at the beginning is predominantly liquid, we will just have the mass of water total divided by the density of water. And again, this would substitute for the volume of the liquid here. So this would then be over the ideal gas constant times our initial temperature, since we are looking at the initial situation here. So we have this relationship here as well. Now the last relationship that I will show here involves this number of moles of water in the vapor phase. Now we can actually apply the ideal gas law here as well. So I have the number of moles of water in the vapor phase. This will equal the pressure of water at the final temperature. We're at capital T there, so we're not confused. So at the final temperature times the volume of the vapor phase. And this will be divided by the ideal gas constant times our final temperature. Okay? So utilizing the given information we have as our parameters, and also these relationships that we have created here, we can actually use the root solver in Python to determine the unknown values that we have here. So now we'll go into Colaboratory and write the code in order to determine the values. Okay, so welcome back into Colaboratory, and the first thing that I'm going to be doing here before we actually start writing the code is I'm going to insert some pre-written code that will allow us to determine certain aspects of certain substances based on data that we have been given. So I'm going to go ahead and paste this link for the pre-written code, and I'm going to use a command in Colaboratory called git clone. And if I paste this link here, what this is going to do is it's going to clone or download
this pre-written code into Colaboratory so that we have it available to use in this code. Now, since I have already have it downloaded in Colaboratory, I get a message that reads destination path CHE tools already exist. But if you were to do this for the first time, it would clone it and it would put it in your files right here. And see, I have it here, and it is called CHE tools. So now what we need to do is we need to go ahead and insert a line, and we need to basically tell Python where to access this code so that we can bring it in for use. So if we do import sys and do sys.path.insert, what we will need to enter here in these quotations is basically the path telling Python where to go to access this pre-written code. So it's under content, and it is called CHE tools. And the format for this is backslash. So if we do backslash content and backslash CHE tools, this will tell Python where to access it. Now what I'll also do here is import tools.che as CHE, so that we're not writing tools.che constantly, or more than we should be. So I'll go ahead and press Shift Enter here. And now what I have here is I have already entered in the data that we have been given for this problem. So I have the ideal gas constant R, the initial pressure, the initial temperature, the number of moles of water, or excuse me, the mass of the total water, the number of moles of water in the vapor phase, and the final pressure. Now this desired that you see here in these two variable names, that will make sense in a minute. Essentially what we will have is we will have two equations that we need to drive to zero in order to utilize the relationships that we've made and the root solver in order to determine the our unknown values. But now what we need to do is I'm going to go ahead and take a look at this pre-written code that we have. So we need to be able to access this code under a variable name. I'll call that variable name P for props. And if I do P equals che.props, what this will want us to enter in here is an object, or in this case, the substance that we will want to download the data from the pre-written code. So in this case, the substance that we're working with here is water. So I'll go ahead and enter that in. And just to show what this pre-written code allows us to do, if I do p dot, essentially what we can do is we can calculate different aspects of water here. So if we wanted to calculate the vapor pressure, we can do that. If we wanted to calculate the density of water, we can do that. So there's just a bunch of different things here that this allows us to calculate. So it's very useful. Okay. Now from here, what we need to do is define a function that will basically return a vector of our unknown variable. So I'll go ahead and just define the function equation, so EQS, and I'll call that vector vector. And here what I'm going to do is just unpack that vector. Again, this vector will return our unknown variable, so that'll be the final temperature, which we're looking for, and the total volume. So set that equal to vector. And here what I'm going to do is I'm going to go ahead and return and write the two equations that we will want to drive to zero. Now these two equations, the first one will be the final pressure minus the final pressure desired. Okay. Now what I mean by this is, since this here will have to equal zero, since we have set the final pressure desired equal to 200,000 pascals, that will mean our final pressure here will have to equal 200,000 pascals in order for this to equal zero. So utilizing this and the relationships that we have, when we use the root solver tool, that will allow us to return the unknown values that we have. So we can do this as well for the number of moles of water in the vapor phase. So if we do number of moles of water in the vapor phase minus the number of moles of water in the vapor phase desired, okay. And make a typo here. So number of moles of water in the vapor phase. So this will essentially say that the number of moles of water in the vapor phase, this will have to equal 0.3 for this equation to equal 0. Okay, so now what we need to do, like I said, is go ahead and enter in the relationships that we have previously determined on the whiteboard. So the first equation or relationship that we'll go ahead and talk about the final pressure. And remember, that was equal to the partial pressure of air plus the partial pressure of water. Okay? Now, we know that the partial pressure of air, we used the ideal gas law. So we say that the partial pressure of air, again, PV equals nRT. So we said that the partial pressure of air equals the number of moles of air times the ideal gas constant R times the final temperature, and this was divided by the volume of the vapor phase. Okay, so we have that. Now we also had a relationship for the volume of the vapor phase, which was, so the volume of the vapor phase equals the total volume, so V total minus the volume of the liquid phase. Okay. Now if you remember, we also had a relationship for the volume of the liquid phase. So the volume of the liquid phase, that equaled the mass of the water in the liquid phase divided by the density of water. So we can say the mass of water, mass of water in the liquid phase divided by the density of water. And this is when we can use the pre-written code that we have added in. So if we do P dot RHOL, this will return the density of water. So we want this density at the final temperature. So we can have that entered in. Okay. Now we also have a relationship for this number of moles of water in the liquid phase. So the number of moles of water in the liquid phase, if you remember, that equals or not the number of moles of water, is the mass of water in the liquid phase. So the mass of water in the liquid phase equals the mass of water total minus the mass of water in the vapor phase. Well, we know the mass of water in the vapor phase equals the number of moles of water in the vapor phase times the molecular weight of water. So we can enter that in. And since we have the number of moles of vapor phase desired equal to 0.3, that is what we'll enter in here. So the number of moles in the vapor phase desired, and this will be multiplied by the molecular weight of water, so 18 times 10 to the negative third. Okay. Now, if you'll notice here, one thing that we still don't know is this number of moles of air. However, we do have a relationship for that as well. And for this, we use the ideal gas law. So the number of moles of air, again, using PV equals nRT, and looking at the initial situation, we had that the initial pressure, the total initial pressure, minus the partial pressure of water. So here, again, we can use the code that we have downloaded in. So if we do P dot PVape, this will give us the vapor pressure of water. So we want this at the initial temperature, so we'll do Ti. And this is multiplied by the volume of the vapor phase, which we know is V total. And since we said at the beginning that the water is predominantly liquid, we had here that the mass of water total, it was just the mass of water total divided by the density of water. So again, we'll have P dot RHOL, okay, We'll have that at the initial temperature since we're looking at the initial situation. And this entire thing will be divided by the ideal gas constant, R, times the initial temperature. Okay. Now the last thing here that we don't know is this partial pressure of water. However, we can calculate that using the pre-written code that we have. So we can do partial pressure of water equals P dot P vape. So this will return us the vapor pressure for water. And we will want this at the final temperature, so enter that in. Let me go ahead and run this just so we have that available. Okay, now the last relationship that we came up with was this number of moles of water in the vapor phase. And we also use the ideal gas law for this too. So the number of moles of water in the vapor phase, again using PV equals nRT, got that the partial pressure of water times the volume of the vapor phase, and this was divided by the ideal gas constant times our final temperature. Okay, let's go ahead and run that and make sure we don't have any errors that we can see. So we're good there. So now we are going to, now that we have entered in the relationships that we have and we have the two equations that we want to drive to zero, we can use the root solver for our function. So if we do root, or actually before I can use this, I have to import root from SciPy optimize. So I'll do from SciPy optimize import root. So it'll be able, or that will allow us to be able to use the root function or the root solver. So if we do root for our function here, and we will need an initial guess for our final temperature and the total volume of the container. So I'm just going to guess 350 for the final temperature and 10 for the total volume. So if I press Shift Enter here, now we get a message that reads back, the iteration is not making good progress. So this basically means that our initial guess is not close enough. So I'm going to go ahead and lower this down to 0.1 because we need the solution to converge correctly. Okay, so here we get that the solution has converged and it returns an array of two different values. Now, these values that it returned, the first one, again, is the final temperature, and the second one is the total volume of the container. So for this problem, we have now determined the unknown variables. So the final temperature that we heat the container to is 366 Kelvin roughly, and 0.012 cubic centimeters. So now, using the root solver, entering in our relationships that we have determined through the variables, we have been able to determine the temperature that the system was heated to and the total volume of the container. So that concludes this example and this video. Thank you for watching.